We all know Newton's third law of motion. Every action has an equal and opposite reaction, or in our case, over here it's force. But what's the source of it? Why does it work this way? To understand that, let's understand law of conservation of momentum. When a collision occurs, the objects exchange or transfer momentum. By law of conservation of momentum, total momentum in a system stays constant. That is, no momentum is added or removed. Hence, some of these changes of individual momentum will also stay zero. By that, we get delta P1 is equal to negative of delta P2. Here is what it exactly means. Delta P1 is positive and equal to negative of delta P2, meaning when delta P1 gains momentum, the blue ball gains momentum, the red ball loses momentum. But what happens when the blue ball loses momentum? In that case, red ball gains momentum. How? Minus of minus is positive. Hence, there is going to be a positive change in the momentum of the red ball. After applying Newton's second law, we get F1 is equal to minus or negative of F2. Since these are vectors, over here F1 and F2 are equal and opposite in direction. Over here F1 is applied on the red ball and F2 is applied on the blue ball as it's in the opposite direction. From this we get it. Newton's third law is just a consequence of law of conservation of momentum. We get this result because the system is trying to conserve momentum. It's following this law. Now the next question is why does law of conservation of momentum even exist? The answer to that question lies in symmetry. Let's discuss spatial transition symmetry first. I have a blue ball and I apply a certain force on it. It gains a momentum P1. We performed this experiment. Now there's another identical ball away from the blue ball. It's not at the exact same site. We apply the same amount of force and it gains a momentum P2. Over here space is continuous and hence it does not matter where we apply our force as long as we apply the same amount of force on identical objects, the momentum they gain will be the same. Hence, the laws of physics stay the same everywhere, no matter where the experiment takes place, as long as the system is continuous. The next symmetry which we are going to discuss is rotational symmetry. What does it mean? Let's first perform an experiment. We have a blue ball over here, we apply a certain force on it, and then it gains a momentum P1. By rotating, what we mean is we rotate everything involved in the system, the space itself and the objects in it. Everything is rotated by 90 degrees and we perform the same experiment again. Same ball, same force. We get the momentum as P2. We again rotate everything in the system by 90 degrees and we perform the experiment. As you can see over here, we apply the force on the ball and the momentum here is P3. Now what we observe over here is P1 is equal to P2 and that's equal to P3. Because we applied the same amount of force and the ball's mass was also the same. Hence, laws of physics stay the same no matter what orientation we follow, and that's all which rotational symmetry is about. Now, the final symmetry which we are going to discuss is time symmetry. Let's perform our experiment. We apply force on a ball and then it gains momentum P1 at 10 a.m. and then we perform the same experiment in the same location with the same ball at 10 p.m. and then we apply the same amount of force and then it gains a momentum P2. Over here P1 and P2 will be equal as we had the same ball with the same mass and we applied the same force. Hence, physics does not change with time in similar conditions. Laws of physics stay the same with respect to time in a continuous system. Now, why are we discussing symmetries in all of this? The answer is Noether's theorem. It states that in a continuous system, all the symmetries correspond to exactly one conserved quantity: translation symmetry, momentum conservation, rotational angular momentum. Time translation symmetry, it corresponds to energy conservation. Let's see Newton's first law. It's valid within a perfect inertial frame. In a similar way, Noether's theorem is valid when our universe satisfies these symmetries. We'll get to it later. However, why are these laws local and not global? In our lab, these symmetries hold on, but globally, the universe is expanded. It's not continuous. Time translation symmetry fails globally. Energy is not conserved across the universe. Hence, we can conclude that these laws are local. They do not govern global events. Newton's third law isn't fundamental. Momentum conservation is symmetries locally in our universe. Thanks for watching this video. I really hope you enjoyed it and understood the concept clearly. Make sure to like, share, and subscribe. And if you have any doubts, feel free to comment below.